This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
Good morning. Happy Valentine's Day. You're here for the love of science, correct? Welcome to the second presentation of Science on Saturday at the Bankhead Theater. These presentations are produced by the Lawrence Livermore National Laboratory with the help of top-notch scientists and local science educators. Last week's topic was the processes, the viewpoints of shale oil and gas production. Our topic today is above ground, though, making electricity out of thin air. We have all seen the wind flowers that dot our surrounding hills. Many of these windmill farms were in the forefront to prove wind power is a viable alternative for energy. Now, state-of-the-art technology has made huge improvements in the wind power production, along with solar power, to cleanly power our world. Today, Doctors Jeff Marocca, Suzanne Singer, along with science educators Tom Scheffler and Eric Carpel, will discuss green power generation. Clean power generation that in time could replace our dependent need for dirtier fuels for power production. Dr. Marocca is an atmospheric scientist and technical leader of Lawrence Livermore National Lab's Wind Energy Research Group. Jeff was part of a team that studied turbine wake and inflow to help attain aggressive state and national targets for renewable energy. Dr. Singer, also of Lawrence Livermore Lab, is involved in a variety of projects that include energy efficiency and renewable energy. One of her passions is to bring sustainable energy to Indian tribes around the country. It has been her goal to improve the lives of Native communities using knowledge she gained from her science, technology, engineering, and math education, STEM. A respected science educator, Tom Scheffler of Granada High School found his love for teaching while in graduate school and has been part of many Science on Saturday presentations. Eric Carpel teaches astronomy and physics at Las Positas College. A graduate of UC San Diego and UCLA, Eric has been fortunate to have worked in places as Sweden, the Stanford Linear Accelerator Center, and the Lick and Keck Observatories. Please welcome Jeff, Suzanne, Tom, and Eric.
All right, are we ready to talk about a little science? It's great to see you all. So today we're going to talk about energy. So let's start with a definition. Energy, what is it? Well, energy, as we know, is what we use to be able to do work, any kind of work. For us as human beings, we eat food to get energy so that we can move ourselves around. We use energy for lots of other things. In fact, we use tremendous amounts of energy. We use energy, for instance, to drive in cars. Everyone drives everywhere. We use energy to fly in airplanes, to visit people, to travel for leisure. We build huge cities that we live in, beautiful cities, but these require a lot of energy to build and to maintain. And in addition to that, we all have our gadgets that are ever multiplying in number that we have to plug in somewhere to get electricity from to recharge. So we love energy, we use a lot of energy, and we're going to keep using more energy. We're going to keep using more energy as individuals because even as cars are getting more efficient and planes are getting more efficient, households now have more cars than ever. People fly more often than ever, and we're using more and more gadgets all the time. So how do we get the energy to power all of these devices, to build these cities, to move ourselves around? Well, most of it today comes from coal, oil, and natural gas. Is this a problem? Well, today's talk is going to address some of the issues and try to get to the answer to that problem. So first, let's try to figure out how much of this stuff we use. Eric, can you tell us a few things about this?
Sure. It probably won't surprise you to see that in the United States, about a third of our total energy use is from petroleum. Most of you know the refined form of petroleum known as gasoline that we use to power our cars. The other two big slices of the energy pie you see here are natural gas and coal. Was anybody here last week to see the talk on shale? Fantastic. Well, then you probably remember that natural gas is a lot cleaner than those other two forms of fossil fuel. But nevertheless, natural gas is far less clean than solar and wind. Those little slices you see up there about 2 o'clock. Now those may seem like pretty small slices of the energy pie, but Wait a few years. Engineers and scientists like Jeff and Suzanne here are working to increase those slices, so in the coming decades, that pie will look very different. How many of you live on a planet besides Earth? A few of you. Thanks for coming.
They got it here in a spaceship.
Yeah. So, really, it's kind of important to look at the global energy picture because we all share the same atmosphere. So, our air is the same air as people in India, China, Africa, South America. Even if you're in Antarctica, it's the same air. So, looking at the energy picture, about a third of the world's use of energy is petroleum. And you might ask, how much petroleum does the world use? Well, one way to look at that is if we were to try to fill up a volume of space with a year's worth of petroleum, that volume of space would be a cubic mile. Can you imagine that? Filling up a cubic mile with oil. That's how much the world uses in a year. In case you're wondering, a cubic mile has a length of 14 football fields on each edge. How much energy is in a cubic mile of oil? Well, huge amount. Instead of giving you a number, let's just call that a cubic mile of oil energy equivalent, or a CMO. Right? So we use 1 CMO of energy from petroleum. The world uses another CMO of energy from coal. So you can imagine another cubic mile essentially of coal. And every year we use almost another cubic mile, actually about 60 or 65% of energy from natural gas. Right? So what do these 3 types of fuels have in common? Well, first of all, they're all fossil fuels, right? Meaning when they were produced hundreds of millions of years ago for the most part, and when they're used up, they're gone forever. What else do they have in common? Well, we generally burn them, right, to release the energy stored in the chemical bonds, to make kinetic energy, to make our cars go, or to boil water to make steam, to turn turbines attached to generators to make electric power. Right? And finally, another thing they have in common is when we burn them, we produce carbon dioxide. Lots and lots and lots of carbon dioxide. Can you imagine setting that cubic mile of petroleum on fire? How much carbon dioxide that would produce? More than the cubic mile. Same with coal. Can you imagine setting that cubic mile of coal on fire? What about natural gas? That's how much we're doing every year. And as the population increases and more people want to use energy, we'll be wanting to use more of these cubic miles every year, perhaps as much as 2 more in the next 20 years. So 2 more cubic miles a year. The question is, are we going to be able to do that without using fossil fuels? And maybe even replace at least one of these using wind and solar. So that's our challenge, and that's what Jeff and Suzanne are going to talk to you about a bit more today.
So today we're going to talk about, first, the greenhouse effect. Right? We've all heard that Earth has a greenhouse effect. So the way a real greenhouse works, one that we would build in our backyard, is that there are panes of glass that are transparent. The sunlight comes through. It hits the interior of the greenhouse, warms up the air in there, but then that air can't escape. The Earth has something like a greenhouse, but it's a little bit more subtle than this. And that's what we're going to talk about next. So what are the origins of the Earth's greenhouse? Well, as we said, inside of a greenhouse, it's warmer. Well, how does the Earth get its energy? So here's a picture of our planet, the Earth, sitting in space. And our Earth is lit. It's lit because it's receiving energy. It's receiving solar radiation. That's the energy source for the planet Earth. So we can see it because it's receiving that energy. But how much of that energy gets here, and how does it get here? That involves the sun and space, and I'm an atmospheric scientist. I'm not an astronomer, but we have an astronomer here, and maybe he can explain that to us as well.
So, about 93 million miles away from here is a fusion reactor as big as 1 million Earths. Do you guys know the name of that fusion reactor? It's the sun, right? Luckily, radiation, those 4 times 10 to the 26 watts that sun is emitting, spread out according to the inverse square law. If you don't know what that means, you can kind of see a representation here. It means that the sunlight spreads out. So the farther away you are from the sun, the less power each unit area, each square meter receives. By the time you get to the Earth, 93 million miles away, each square meter receives about 1,400 watts. So what does that mean?
Well, I think most of us are familiar with what a 100-watt light bulb looks like. This is the kind of light bulb that you might have in any reading lamp at home. Well, this poster board here, it's not quite a square meter, but it's almost a square meter. If I shine the light of this light bulb down on this poster board, I'm taking 100 watts, illuminating 1 square meter, we have 100 watts per square meter. If I wanted to recreate the light we get from the sun, I would need about 14 light bulbs like this, all shining on the same piece of poster board in order to get that 1,400 watts per square meter. This is what we get from the sun.
All right, so another thing we have to ask ourselves is does the Earth absorb all of that radiation? Well, the answer is no. We have to consider something called planetary albedo, which is the amount of radiation reflected relative to the radiation received. So an albedo of 1 means that all the energy is reflected, such as this white surface here. But if you have an albedo of 0, it's something like a black body, but you can't actually see because it absorbs everything and doesn't reflect anything. So the Earth is somewhere between that. Oh, sorry. And it's about 0.3, and that's because we have things like clouds or shiny surfaces in the atmosphere. So if we take roughly 30% of this 1367 watts per meter squared, about 410 watts per meter squared gets reflected, and the remainder gets absorbed.
So, what do you think might be more important for the total amount of solar radiation received on the surface of a planet? Its distance away from the sun or its albedo? Well, here's a picture of the Earth and Venus. We know that Venus is closer to the sun than Earth is. Therefore, Venus should get more radiation than the sun. And in fact, it does. It gets about than the Earth. And it does. It gets about twice as much radiation as the Earth. But because the albedo of Venus, due to all the shiny reflective clouds, is about 2.5 times higher than that of the Earth, we actually end up with less radiation reaching the surface of Venus than we do the Earth. Only about 2/3 as much radiation gets to the surface of Venus, even though it's getting twice as much at the top of the atmosphere. Venus and Earth are sitting in space. They're absorbing radiation. We've just figured out how much radiation they're getting. So how warm is that going to make them? Well, what happens to you when you stand out in the sun? You heat up, right? But you don't keep heating up forever until you melt and vaporize. No, you heat up and then you stop. And why do you stop heating up? The reason for that is that just like the sun, you're radiating too. Everything in the universe that we know about that has a temperature radiates. And it radiates according to a constant times temperature to the 4th power. So it's proportional to the 4th power of temperature. That's a really fast change of radiation in response to temperature. If you doubled the temperature, it would be 16 times more radiation. So as the Earth heats up, or Venus, or you start radiating very rapidly, much larger amounts of radiation, until eventually the radiation that you're emitting is equal in amount to the radiation that you're receiving from whatever's illuminating you, in this case the sun. And that's the definition of radiative equilibrium. R in equals R out.
So we've got a couple of little golf balls here, a couple spheres, a white one and a black one. Now those of you who've worn white t-shirts and black t-shirts outside on a sunny day in the hot summer, which of these do you expect to be the hotter one? The black one. Well, let's see. I have an infrared thermometer here. The white sphere is at about 120, 104 degrees. My point at the black sphere, 160 degrees. So both are receiving the same amount of light from the lamp here, but because the white sphere has the higher albedo, the higher reflectivity, it reaches this radiative equilibrium at a cooler temperature than the black sphere does. Well, these are a couple of small spheres with different amounts of reflectivity, different albedos. Let's talk about some larger spheres with different albedos.
All right, so can we determine the temperature of 2 objects in space, 2 planets, instead of these 2 spheres on the table? As a matter of fact, yes, we can. We've already calculated the amount of solar radiation reaching the surface. We know that those bodies are going to radiate in direct proportionality to their temperature. We know that the amount radiated away needs to be equal to the amount that it's receiving. So all we have to do is a little bit of geometry and solve for the temperature. And you get the radiative equilibrium temperature of each of these planets. And when we do this calculation, we get a radiative equilibrium temperature of minus 51 degrees for Venus and minus 1 degrees for Earth. Sound reasonable? That doesn't sound very reasonable to me. Doesn't that seem kind of cold? I mean, have you been outside? I mean, it's almost like this here. But there are places like this all over the planet. If our globally average temperature was minus 1 degrees, there wouldn't be very many places like this. And how about Venus? Isn't Venus supposed to be hot enough to melt metals? How can it be minus 51 degrees? So an important thing that we all have to keep in mind when we're doing a calculation is that when you get an answer, check the answer against sanity, right? These answers are not, they don't pass the sanity test. So what did we do wrong? Well, we didn't do the math and the physics wrong. We can check those calculations and make sure they're right. So what we have to ask ourselves is, whenever we're solving an equation, is two things. Are we solving the equation correctly? And are we solving the correct equation? Well, we must have missed something in our calculation because we're solving the equation correctly. So what could it be? There has to be something different. And it turns out that there is something different about that explains this discrepancy. So when we stand outside in the sun, we can see, right? We're seeing in the radiation field that comes from the sun. We're seeing in wavelengths of visible radiation that are coming from the sun, coming through our atmosphere and illuminating our world. When we go out at night, can we see? Not very well, right? The Earth is radiating too, but it's not radiating at that same range of wavelengths, is it? Because we can't see, unless we use something like an infrared thermometer or night vision goggles or something like that. So perhaps this holds a clue. Maybe there's something about the wavelengths of radiation that's important. So let's learn a little bit more about this.
Well, here we have another light bulb, very similar to the one that we were using a moment ago, except this one's hooked up to a variable voltage. So instead of just on and off, I can slowly crank it up. So notice it's not glowing yet. I start to give it a little bit of voltage, and it's barely lighting up. It's kind of reddish right now. It's about the same color as the red burner on an electric stove, and it's the same color for the same reason. It's literally red hot. Very different reason than, say, a fire truck would be red. A fire truck is red because it's got red paint on it that reflects red light. This is so hot it's glowing red. Well, if I turn up the voltage a little bit more, it starts to become brighter, starts to look a little more orange. Go even hotter, starts to become kind of yellowish, and eventually it's so hot, it's emitting light from all the colors of the rainbow and it looks white. So it is literally white hot right now. Well, imagine reversing this process. So it's very hot right now, I wouldn't want to touch this light bulb. If I turn it down, it goes from being white to yellow. It's not quite as hot, but it's still hot that it's glowing. A little bit cooler, it's still glowing orange. A little bit cooler, it's back to red, so now it's only as hot as a burner on an electric stove. Turn the juice a little bit down. I don't see light anymore, but this is still hot. I wouldn't want to touch this. So it's still glowing, it's just not glowing like we can see. It's actually glowing in the infrared. And it turns out that's what the Earth is doing, and that's, in fact, what all of us are doing right now, is we are glowing in the infrared because of our temperatures.
So this answers our one important question about the difference of the radiation. Here we're showing the distribution of the wavelengths of radiation coming from a hot object like the sun. Remember, the wavelength is just the distance of the wave train across two adjacent crests or troughs. And all electromagnetic radiation, whether it comes from the Earth or the sun, is in the form of a wave field. So we also can find that the peak wavelength at which the most radiation is emitted from a body is inversely proportional to temperature. It's B over T. That means if you have a very hot object like the sun that has a temperature of 10,000 or so degrees Fahrenheit, those wavelengths are going to be very short. However, when you have an object like the Earth that's supposedly -1 degrees, that radiation is going to be at much longer wavelengths, and in fact, it is. And as he showed us when he turned the light down, below red is infrared. Infra below. And that's where the Earth's radiation spectrum begins. So, great, we've learned something really important, that radiation from the Earth and the sun have different wavelengths. Why does that matter? We're trying to understand the origins of the Earth's temperature and why we got the wrong answer when we simply looked at the radiative equilibrium temperature. The key to understanding this is that both of these forms of radiation have to come through the Earth's atmosphere in order to get here. Right? Does the atmosphere of the planet play a role? Well, it turns out that gases interact selectively with radiation. In other words, different gases will absorb and emit different wavelengths of radiation, but will be completely transparent to others. Other stuff can pass right through them, just like an X-ray goes right through your skin and lodges in your bone. On our planet, our atmosphere is a mixture of gases. We call that air. And it consists mostly of nitrogen with some oxygen and a little tiny sliver of other stuff. Well, it turns out that the nitrogen and the oxygen don't interact strongly with either incoming solar radiation or outgoing Earth radiation. That's kind of intuitively obvious. When we go outside during the day, it's not dark. Nothing is absorbing the sunlight. And although you can't see it, if that was all there was in our atmosphere, the Earth would simply radiate all of its energy back to space, and we would have the radiative equilibrium temperature that we calculated a few slides ago. But because we have an atmosphere that has other things in it, this doesn't happen. Most of this other stuff, which is a small amount, is carbon dioxide. And carbon dioxide, as we all know, is a greenhouse gas. What that means is that the solar radiation coming into the planet comes through the atmosphere and doesn't interact with carbon dioxide molecules. However, the radiation that escapes from Earth and tries to get back out to space does interact with the carbon dioxide molecules. And because of that, some of that outgoing radiation is absorbed by those molecules and it's re-emitted, and some of that re-emitted radiation goes back down to the surface of the Earth, warming it up a little bit more, and it also warms up the atmosphere, and less of that total radiation goes out to space. So this is the origin of the greenhouse effect on Earth, and this explains why, when we ignore the atmosphere, we get the wrong answer. It's not because we did the wrong calculations, it's because we didn't include relevant physical phenomena that were important to getting the right answer. Once we correct for the omission of the Earth's atmosphere and include that in our calculations, we recover the observed average temperature of Earth. So going through all of this, it seems a little arduous, but it makes the point that this little tiny sliver of other stuff, just a few hundred parts per million, can significantly change the temperature on the surface of the Earth and of the atmosphere by 60 or so degrees. So that explains what's going on at Earth. Where's our Venus expert? I wonder if this explains what's going on in Venus.
Thanks, Jeff. So those of you that came here from off-world, I suspect that none of you came from Venus. It would be a little difficult to live at 864 degrees Fahrenheit. Not only that, if you tried to take a breath of the atmosphere, 96% of the air you'd be breathing was carbon dioxide. That's not the whole story, however. The atmosphere of Venus is also 100 times thicker than the Earth's atmosphere. So 96% of 100 times thicker atmosphere means there's thousands and thousands of times more carbon dioxide on Venus than there is on the Earth. At this point, you might ask yourself, why exactly is Venus making an appearance in our talk on fossil fuels and solar and wind? And of course, the answer has to do with carbon dioxide, right? All that carbon dioxide on Venus produces what's called a runaway greenhouse effect, meaning that the sunlight that penetrates through the atmosphere hits the surface, warms the surface up. As Tom was showing you, it starts to glow in the infrared. That infrared radiation is reflected and re-reflected back down to the surface, reheating the surface and reheating the air many, many times until Venus reaches this incredible temperature. Now, on Earth, we're emitting quite a bit of greenhouse gas, quite a bit of carbon dioxide ourselves, and so it's worth talking for a minute about why Venus has so much carbon dioxide and then you can ponder whether the Earth is headed in that direction. And we need to understand that. We need to go back billions of years to when the Earth and Venus both had lots of water. But Venus has always been closer to the sun. And so the water that was on Venus was gradually being destroyed by the sun's ultraviolet rays. That doesn't sound good, does it? Luckily on Earth, that didn't happen. It continued to rain on Earth, and the rain washed carbon dioxide into the water, where plant life evolved to produce oxygen. The oxygen produced ozone, and the ozone protected not only the plant life, but it also protected the water vapor in the atmosphere, so it didn't get destroyed by ultraviolet. What about Venus? Well, that didn't happen on Venus. The water vapor got destroyed by ultraviolet light, and there came a day billions of years ago, perhaps, maybe as recently as 1 billion years ago, when it never rained again on Venus. After that, the carbon dioxide that was accumulating in the atmosphere from volcanism continued to accumulate and accumulate and accumulate and accumulate and accumulate until it produced the runaway greenhouse effect we see today. This is something we'd very much like to avoid here on Earth, so perhaps Jeff can tell us a little bit about whether that's a possibility.
So that's a pretty scary tale, and we're not here to try to tell you that that's what's going to happen. The fact is, we're really not sure what's going to happen. The Earth is a very complicated system with a lot of moving parts, and making predictions about future climate is not easy. That goes for both gloom and doom scenarios, and also everything is going to be okay. So if we do get to a point where we're like Venus, when we're swimming around in 4 times, how many thousands of times the Earth's atmosphere of weight, of mass, crushing our bones and toxifying us with 97% carbon dioxide, temperature is going to be the least of our worries. But it's worth thinking about, okay, well, what if we don't go all the way to Venus? What if we just change the greenhouse effect by a little bit? I mean, it's beautiful outside today, right? Doesn't everyone seem to like warm winters? So how's that working for us? Well, as scientists, we should try to assess the changes that we're seeing in response to the experiment that we're performing on our only planet before we decide whether or not it's a good idea to proceed. And I would mistrust anybody telling you that everything is going to be okay, because we just don't know. So let's see what we're actually observing rather than speculating about what's going to happen in the future. Well, here's a picture of Arctic Ocean sea ice extent in the summer from 32 years ago, and then from 32 years ago minus 3 years. And we're seeing that there's significantly less ice covering the Arctic Ocean during the summer. Okay, this is pretty removed from everyday experience, right? Not that many people live in the Arctic, but some people do, and they like to have a habitat up there. And to think that we're not connected to the Arctic is foolish, because the whole global atmospheric system, as Eric said earlier, is connected. We all breathe the same air. We all have the same pollution, whether we're here, in Africa, in Asia, doesn't matter. This water that is melting from the sea ice and other glaciers that used to be stored on land is draining into the oceans. And what that's doing is it's raising ocean levels everywhere across the globe. And this is going to be challenging for those of us who have grandparents who retired in Florida, or those of us who might want to do that someday after lucrative careers as scientists. This is a map showing how much of Florida is going to be inundated by sea level change in just a few decades if we keep on enhancing the greenhouse effect at rates that we're currently doing. And it's not just the level of the ocean that's changing. The ocean water is changing as well. Much of the heat that we're putting into the atmosphere is going into the ocean. Not only that, the carbon that's washing out in the rain, as Eric described, is becoming stored in the oceans as well. And in fact, you've probably heard that the oceans are acidifying. They're becoming not only warmer, but they're becoming more acidic. And that's making it really hard for creatures that like to build shells and corals and other things that live in the marine ecosystem that support the entire marine ecosystem. It's making it harder for them to live. And we are not separated from these ecosystems. They're underwater, but they're vital to us. So what do? We like our cars. We're not going to give these up. We like to live in beautiful cities like this that require tremendous amounts of energy. We like to fly in airplanes. We love these things. We'd eat them if we could. But powering all of this is polluting the atmosphere. We're burning coal, oil, and natural gas. So is there an alternative? Is there something else that we can do instead? Well, we're going to talk about a couple of those. I'm going to talk about wind.
I'll talk about solar.
And we're going to see what wind and solar can do. Now, preemptively, I'm going to say there are a lot of other forms of green technology that we could be looking at. We're going to focus on wind and energy for a few reasons. One, you can see evidence of them all around here. You can see the wind turbines in Altamont. You can see solar panels around here. In Southern California, you can see giant solar, industrial-scale solar plants. Also, these are technologies that are deployable at scale today that can make a huge difference in those cubic mile of oil equivalents that Eric was talking about. So before we go into talk about wind energy, let's first look at how we make power today and how wind turbines can make power instead of what we're using today.
I was wondering if you wouldn't mind simulating, well, providing the energy that we need to turn this crank that's attached to a generator to power this light bulb. So can you give that a whirl? Can you do a little faster? Not too much fast, kind of in between. A little faster, there you go. So keep doing that for a while. Notice Parker's not having too much trouble. And you also notice this light bulb isn't lighting up. Right? Well, what happens, that's because I haven't connected the circuit yet. So what happens if I connect the circuit? So let's connect that circuit. You guys keep an eye on the light bulb and Parker. Did you notice any difference there, Parker? What happened? Got tougher. And now Parker's got that light bulb going. So Parker, keep that light bulb going. Don't stop. Right now, Parker's using his muscles to provide the kinetic energy you need to turn that turbine to generate electrical power. Instead of boiling fossil fuels. Are you okay there, Parker? Yeah. Good. Instead of using fossil fuels to do this, to burn fossil fuels to boil water to make steam to turn a turbine connected to a generator, we can use Parker. Okay. But remember, you don't get something for nothing. And Parker's getting probably a little tired right now. So what happens if I disconnect that circuit? Did you notice how that got a bit easier, didn't it? Yeah. Okay, well thanks, Parker. I think we'll give you a rest now. And so that shows you don't get something for nothing. Hey, Parker. All right. Okay. So we can burn fossil fuels to boil water to turn turbines connected to generators to make electric power. We can get Parker or all of you and thousands of audiences like you to turn turbines. Or we could use kinetic energy from another resource we have. Can anybody think of one that might be available? What's that? Wind. Is there someone that could provide some wind for me? Tom? Jeff? Jeff's a...
I'm a wind guy.
Oh yeah, Jeff's a...
And I love to vacuum.
Okay.
This is the inverse vacuum.
Yes.
This actually blows out.
Okay, so we have here a very small wind turbine. A little smaller than the ones you see outside, but still wind turbine. And we're going to use the kinetic energy of wind to turn this turbine. And look, it's almost like a Parker of energy right there. Right? Lighting our little light bulb. There you go. Okay. So now, this is a turbine. This is a very small toy turbine, and we're lighting. Well, it's a real turbine attached to a real generator, but it's a very small scale. And this light bulb that we're powering uses less than a watt of energy. What can we do on a much larger industrial scale to power our homes and our cities and our future?
All right, well, I work on this kind of stuff at the lab, so I'll tell us a little bit about modern industrial scale wind turbines. So these things stand very tall, around 100 meters on towers. They have blade diameters that are very large. Let's see why they're so large. First, let's understand how they work. So one of the differences between a real utility scale turbine and the one that we looked at is the shape of the blade. Wind turbines have very uniquely shaped blades. They're very long. They change shape as you go down the length. And if you look here on this image to the right, to the lower right, you'll see there are cross sections of the blade. These are familiar shapes to aerodynamicists. They're called airfoils. Airfoils have a particular property that when the blade moves through the air, the wind flows over the wing and generates a force called lift. We're all familiar with this because we've all flown in airplanes before, right? So the pilot of an airplane is able to generate enough lift by moving quickly enough through the air, or also by changing the angle of attack. The angle of attack being the angle between the chord line of the blade, the line running down the middle of the blade, and the velocity hitting the front of the wing. So what's true for airplanes is true for wind turbines. In wind turbines, we want to use that lift force as it flows over the wings, or the blades in this case, to generate a lift force that's in the same direction. So why don't wind turbine blades look just like airplane blades? Well, because there's another component of motion that has to be considered as well. What really drives a wind turbine is the wind blowing into the front of the turbine. As the turbine turns, it induces another component of the flow that you're seeing pictured here with the pink arrow. And it's really the combination of those two forces that defines the resultant vector, which is what you would feel if you were on the tip of that blade. The angle is a little bit different. But just like the pilot can change the angle of attack and to some extent change the speed of the aircraft, the control system in a wind turbine can pitch the blades. And as you can see, you can also, the blade shape also changes as you go in radial length down out towards the tip, due to the fact that the tips are moving in the circle faster than the areas near the blade root or near the hub. So this explains something that's really interesting about turbine blades. They're very sophisticated machines, and they extract power very efficiently. How efficiently? Well, we can talk about that on the next slide. So here's an equation. This equation looks kind of complicated, but it's actually really simple once we cast it in terms that everybody's familiar with. And you'll see that you can really understand well the power that you can get out of a wind turbine based on a couple atmospheric variables and a couple of engineering variables. Well, the first one is V. V is the symbol that we use for the wind speed. Of course, it's a wind turbine, so you would expect the power to somehow depend on the wind speed. What's interesting is that it depends on the wind speed cubed. So there's a very fast change in the amount of power you can produce with a small change of the wind speed. Another term in this equation, another atmospheric term, is the density. The density of air is the mass of all of the molecules of gas that are in that air over the volume, a given unit volume of the air. So we know from physics class that kinetic energy is 1/2 mass times velocity squared. And as Eric told us, it's the kinetic energy from the flow that we use to make electricity to spin the turbines. Well, for a fluid system, the unit of mass is in the volume. So we have a kinetic energy per unit volume that's 1/2 rho v squared. And you can see that those terms are both in our wind power equation, as they should be. However, that's kinetic energy, and we care about power. So there are a couple of other terms in the equation, namely the area of the disk, that converts us from kinetic energy to power. The area of the disk is the area of the circle that's swept out by the blades as they rotate around in the plane of rotation. And like any good circle, the area is pi r squared. In this case, r being the blade length, the length of each individual blade. So we have, in these terms, so far figured out how much power is available to be captured within the air flowing through this disk at this velocity with this density. How well do we capture that? Well, that's captured in this power coefficient that determines the efficiency of the turbine. And this generally ranges to around 0.3, 0.4. It has a theoretical limit of a little bit over 1/2. So we've got a ways to go to harness all of the energy. We'll never be able to get it all, but this is where the engineering sort of comes in. This is where the shape of the blade matters. This is where the operational system that pitches the blade or yaws the turbine in and out of the wind can make a difference. So this equation can tell us a couple of very simple, obvious things that describe why modern wind turbines look the way that they do. They're on tall towers. Because if you double the wind speed, you end up getting 8 times more power because it's 2 cubed times v cubed. Additionally, if you were to double the blade length, you would get 4 times more power because the area is pi r squared, and you're squaring 2r. So you're squaring the 2, right? And if you were able to do both of these things, now you're talking about 32 times more power. So again, this describes why our wind turbines are so tall. This is a typical profile of the wind speed above the surface of the Earth. It increases as you get away from the surface because there's friction and objects at the surface that block the flow. If you get up above all of that, the wind speeds increase. So for this smallish turbine, it's seeing mostly small velocities, which is fine. But if you can make the turbine taller, that turbine is experiencing larger velocities. And remember, this delta V here is cubed. Not only that, you can make the area much larger. So this is why modern wind turbines are about as big and tall as we can reasonably manufacture them on land. And the really big ones are going to go up in the oceans. So we have everything we need to know, right? Well, we need to be able to predict the wind, right? And that's, I mean, you all turn on the news in the morning. I'm sure you're all avid news junkies, right? And the weather person comes on and says what's going to happen, and 3 hours later something different is happening, right? We're not so good at predicting the weather, and we're also not so good at predicting the winds. We're getting better, but we're not there yet. So how do we predict the winds? Well, this is one equation. We have to solve a lot of equations. So this looks kind of overwhelming. I mean, this is a really ugly equation with lots of terms and notation that nobody can possibly understand. Well, actually, you can understand it, and I'm going to prove to you that you can understand this because you already know half of the terms that are in this equation. First of all, everywhere you see a V, that's the wind speed, right? Everywhere you see an R there, that's radiation. We learned about radiation a few minutes ago, right? And what did we learn that radiation influences? The temperature, which is T. And we also learned about our friend rho. So I've already described almost half the terms in this equation. The other notation simply reflects the relationship between these variables in a compact way that anyone can understand if they just take their science and math classes for a few more years. So don't be intimidated by this. Writing these equations down and understanding what they mean isn't the hard part. The hard part is actually solving these equations. We can't solve them analytically. We can't solve these on pencil and paper. We have to solve these on a computer. And also, in order for us to solve these equations, we have to divide up the Earth's atmosphere into little boxes. And inside each of these little boxes, we solve this whole set of equations. But we don't have to solve them just once. We have to solve for a little time increment, and then we have to solve the adjacent cube, and then the adjacent cube after that, because their evolution requires the knowledge of the evolution of their neighbors. It's an integrated system. All the pieces need to talk to one another. So at Livermore, we have these wonderful supercomputers that we can use. A supercomputer, like shown here, consists of banks, each of which might contain hundreds or even thousands of processors, each processor being like your laptop. Well, each of these processors can grab a handful of those boxes, solve the equations for a little time increment ahead. The next processor takes the next batch, and every computer processor takes a little piece of the problem, and they stop and wait for their neighbors, they exchange information, and in this way you can take an incomprehensibly impossible-looking problem, and you can actually solve it on a supercomputer with a little bit of knowledge of math and physics. So this is what many of us do at the lab. What do you get out of this? Well, you get something that looks sort of like the Earth, right? But what we're using the colors and the arrows here to show you are different variables: pressure, temperature, wind speed. These are things that you can go out and measure, but you can't measure them everywhere. But you can look at their distributions inside of a computer model, and you can start to learn about relationships between variables that you can use to do a better job of predicting not just the weather, but the winds too. So this is sort of what a global climate simulation would look like. The whole globe is depicted. But you can zoom in on a smaller area until you can get down to the scale of a wind turbine. Here we're showing a wind turbine in a flow, in a little ravine. The color contours in the background are temperature. Often when you go out at night in the evening, when it gets cold, the cold air sinks down into the valleys, just like it's happening here. And the little vectors in the background are showing you the wind direction. So we can simulate how a wind turbine would behave in this flow. And that's what I'm showing you here. Shown here is a computer simulation of one wind turbine model at the location of the little black vertical lines there. This is height in the atmosphere going up from 0 to about 400 meters. which is about 4 football fields. And on the right is distance in kilometers. Now, the colors in the background, the red colors are the highest velocities, as you can see in the color bar on the right, whereas the bluish colors are the lowest velocities. So the first thing we see is if we look in front of the turbine, where the turbine hasn't made an impact, the wind speeds increase with height, just like the diagram we showed, right? So this model is able to capture aspects of the atmospheric flow. But more importantly, if you look behind the turbine, you see bluer colors. Those are lower wind speeds. Well, it has to be the case, right? Because the kinetic energy is 1/2 mass times velocity squared. In a fluid system, 1/2 rho times velocity squared. But we're taking some of that energy away and we're making electricity with it. And energy is neither created nor destroyed. If we're making electricity, that energy has to come from somewhere. It comes from the kinetic energy, which is why you see lower velocity air downstream of the turbines. So what you can do for one turbine, you can do for multiple turbines. And next time, maybe the animation will show up. So this is what we've talked about so far is using a means of spinning a generator to create energy, whether it's burning oil that turns a steam turbine that turns a generator, or whether it's using the kinetic energy in the air. But there are other ways that you can create energy. You don't necessarily have to spin a generator. Maybe Tom can show us something about that.
So a few minutes ago, we were able to light up a light bulb using the wind supplied by this air pump right here. Here I've got another little light bulb right here, and it's attached to a device called a photovoltaic cell, which is probably more commonly known as a solar panel. Oops. So if I bring in a light source, so you can see I'm turning light from energy from the light into electrical energy, which then powers this light over here. Take it away. And now to tell us a lot more about photovoltaic cells and harnessing solar light, Suzanne.
So I guess I'll sort of talk a little bit about why I'm so interested in science and engineering and renewable energy in general. So this is kind of where my mom grew up. This is my grandma's house at the end of this arrow, and this is the southwestern United States. So her nearest neighbor is somewhere miles away off of this photo. So there's still thousands of homes in this area without access to electricity. So that makes it really important when it becomes expensive to extend the utility grid even just a little bit. So that's why we have to take advantage of technology like solar energy. So this is an off-grid or standalone system. It's about 1,000 watts, and here on the bottom you can see they're looking at the batteries and all the instrumentation, and that's just enough to power up probably some lighting and maybe a small television or radio. Another example of an off-grid system is this small solar panel on the left, and that's powering a tiny television at the Arun village on Lake Titicaca, so that's on the border of Peru. And solar is a great resource for villages like this that are so remote that they are built on reeds. But in contrast, here in California, we have a lot of rooftop solar, and that basically complements or subsidizes what we already use from the utility grid. So I'm curious, how many of you guys have solar on your rooftops? Well, that's great, some of you. So even though more and more people are putting solar panels up, it's still a small piece of the energy pie. So in 2013, less than 1% of the US energy consumption came from solar resources. And so if we want to think about that amount in terms of other energy forms, so let's think about a burrito. Let's say a large burrito has 1,200 calories. So that much solar energy is like the energy contained in 97 billion burritos. But solar energy is not something that's new. People have been using it for thousands of years. So this is a photo of Mesa Verde. So a lot of these communities took advantage of the heating when the solar heats the ground, and that's called sort of thermal mass to keep themselves warm. Other ways they've used it is to use their windows and overhangs to take advantage of the sun. So in the wintertime, when the sun is low, it allows sunlight and heat through. But in the hot summer months, it's high enough to where the ledges block off some of the sunlight. But there are other ways we can take advantage of solar. So this is a picture of Eric standing in front of a sort of a dish of mirrors, and that's focused onto a little pan or stove there. So people take advantage of focusing light to provide heating. But what if we take that and we replace it, let's say, an engine? So if we consume a lot of heat, use that to generate steam, which then drives a steam turbine, and you can generate electricity. So that is some of the technologies that is available now. Another form of concentrating solar power is what you see here on the right. So sort of on the ground is a whole array of mirrors or heliostats that track the sun, and then they focus light onto that little square up there, and that is the power tower. So the receivers up there collect the heat, and they use that, again, to generate steam and generate electricity. But is there other ways you can think of that we can use solar energy? Eric?
So one of the problems with solar and wind is that it's an intermittent resource, meaning that solar energy is available generally when the sun is shining, and solar energy is available when the sun is shining, and wind is usually available when the wind is blowing. So storage of electricity produced by wind and solar is fairly important. Now, you guys all know about batteries. I'm sure you've all been charging batteries at some point, probably in the last 24 hours for your cell phones. There's also electric car batteries and computer batteries. But batteries have their problems, right? You have to make them. They're usually made out of metals. And when they're no longer useful, we have to dispose of them. And think about the millions and millions, even possibly billions of batteries that may be required when we're using wind and solar on a much larger scale. So one alternative to that is hydrogen. I have here a fuel cell. And what a fuel cell is it's called a proton exchange membrane. Right now I'm using solar energy from would-be sunlight to produce hydrogen and oxygen. You probably know this process as electrolysis. And so you can see those little bubbles that you're seeing are bubbles of oxygen and hydrogen that are being produced. Normally there'd be twice as much hydrogen as oxygen, but the system's a little leaky here, so we have more oxygen than hydrogen. Now if I turn that light off, or at least away from the panel, I can still try to recover that energy by putting the hydrogen and oxygen back together through an identical proton exchange membrane. And so in order to do that, I have to open these little stopcocks that let water through. And hopefully we'll get the water's flowing, making a little mess of this. And you can see the panel, you can see the little propeller turning there. So no sunlight, no problem, right? So we can make hydrogen possibly on a very large scale, compress it, transport it when it's needed or where it's needed, and that could be a possible way of storing energy. So when you think of hydrogen, think batteries. Don't think hydrogen itself, but the hydrogen acts like a battery for us.
Here's our waste product. Water.
So this generally will run for a while. Let me turn off the stopcock.
Thanks.
So Eric took advantage of a photovoltaic cell or PV cell, and so we'll talk a little more about how that works. So you typically have sun, like as we talked about, coming in, which hits the solar panel. So these are made of materials such as semiconductors or silicon that take advantage of what's called the photoelectric effect. And so this allows these materials to absorb photons and release electrons. So when you have these electrons, free electrons, they tend to flow and generate a current. And this current, together with the cell's voltage, when you apply it across a load, you can generate electricity. And so something we learned earlier is that the sun comes in a wide array of wavelengths. And this sort of is what this signifies, which is the solar spectrum. So an ideal solar cell would outline the shape exactly, but that's very hard to do. So just to give you an example, some of these blue solar cells you're used to seeing are probably silicon, and so blue line is kind of the shape or the outline that it takes advantage of. So it only uses a small fraction of the solar spectrum to convert sunlight to electricity. And if we look more in depth about what actually contributes to the power of a solar panel, so something you have seen earlier is this term R, or the incident flux, or this amount of solar that actually hits the panel. The power of a solar panel also depends on the area of your collector. So it makes sense if you install more panels, you can generate more power. But this also depends on the efficiency of the solar cell. So just to give you an example, this is a crystalline silicon solar cell, and it has an efficiency of roughly 25%. So this material preferentially absorbs some of the red wavelength of light and pretty much reflects all others. So there's some research into looking into how can we increase the efficiency of some of these cells. So one example is this on the right, which is a multi-junction PV cell. So what it does is it takes 3 layers. So the bottom layer will absorb and convert the red wavelength. The middle layer will do the same with the green, and the top layer is the same with the blue wavelength. So if you can sandwich these all together and take advantage of a broader spectrum, then you can increase the efficiency. So some of the best efficiencies of these types of cells are much higher, around 44%. So this becomes important when you have restrictions, size restrictions, or weight restrictions. You can get the same amount of power from a much smaller size solar cell. But there are other challenges aside from the solar panel to optimizing how much electricity actually goes to the utility grid. So one way you could look at your entire system, all the different components, and figure out where your electrical losses are. But one thing we're trying to do here at the lab is to predict how much solar power will be generated in the future. So let's say an hour from now or a day from now. But there are lots of factors that make that extremely difficult. So let's say we want to look at sort of the atmosphere and what's going on. There's things like pollution and water vapor, clouds and dust. So light gets pretty much scattered by any particulates in the air. But the one thing that's really hard to predict is clouds. And so one of the big challenges is how can we use instrumentation and modeling to figure out where they're going to be in the future and what they're going to look like. So to get a better idea of how renewable energy influences our lives, let's look at our power usage in a single day. So this blue line sort of signifies California's demand, or how much power in megawatts is needed to satisfy our electrical needs. If we integrate solar energy into it, it makes sense that it goes up after the sun comes up and starts to go away as the sun sets. We could also integrate wind energy. It could be variable throughout the day. The tough part is that we don't make enough of these to meet all of our electrical needs, so we need other resources to fill the gap. So that's kind of what this net load is demand minus the renewables, and a lot of that consists of fossil fuels. So one of the challenges we have is how do we efficiently and effectively integrate renewable energy into the grid without wasting too much? What we really want to do is increase both of these lines, solar and wind, so that we can use a lot less net load and a lot less fossil fuels. Another challenge we have is sort of what Eric was alluding to earlier, is how do we store solar power or wind power and use it later? So as we know, solar is only available during the sunlight hours. Your wind could change throughout the day, although it tends to be stronger at night. One example is we can install solar. So that's me helping install a battery bank for a solar panel on the roof. And Eric talked about another possibility is to be able to use fuel cells. So Jeff is going to talk about another challenge.
Another issue that we have is that the resources are not distributed everywhere where we want to use them. This map on the left is showing where are the best solar resources. Those are the darkest colors that you see on the map. And as we would expect, most of those are in the desert Southwest, where we have the lowest latitude, so we get more solar energy, and we have also the fewest clouds due to the atmosphere being very dry. On the right, we have a distribution of where the wind resources are best, and it's the purple, lavender, and red colors that show us where the wind resource is strongest. And notice that these two areas don't necessarily overlap. Not only do they not overlap well with one another, they don't necessarily overlap with population centers. Most of the wind is in what we call the flyover states, where many of us are from but no longer live. How do we get that energy to where the people who need it most can use it? And that's a transmission problem. And unfortunately, it's not as simple as just putting up some more power lines. But that's another one of the challenges. Now, what these show are annual average distributions. Well, we have an annual average temperature here in Livermore, but when you go out on a given day, it's probably not that, right? What we also need to do is be able to forecast what's going to be happening in a few hours, what's going to happen tomorrow, or for the rest of the day. And to do that, we use those things called models that we all love so much. But what is a model by definition? It's an abstraction of reality. It's a representation, but it's imperfect. It's not the real thing. That's true of model cars, model airplanes. You can decide whether that's true of model people. It's certainly true of the models that we use for the atmosphere. So what's being shown here is the output of a solar plant throughout the daylight hours of the day using a bunch of different numerical weather modeling techniques, all of which are equally plausible but contain some uncertainties. This is why the weather forecast isn't always perfect. And when you change the channel, one person says it's going to be 72 and the next person says it's going to be 75. There is some disagreement. And so if you're trying to predict the amount of solar power you want to put on the grid, you want to be able to choose from among those scenarios on the right, or at least express the uncertainty that you have in a forecast in some sort of a usable way. What's true for solar is true for wind. These are all different, equally likely scenarios that we have to choose from. So one of the big challenges for both of our fields is to be able to make better, more accurate predictions so that we can integrate more of this resource as we develop it and it comes online. So here's sort of the choice we have, and it's an inclusive choice. It's not a solid line, it's a dotted line. We definitely want to move away from our fossil fuels, but as we've seen from Suzanne's presentation, we still need some of it. So if you were here last week and you saw Roger's talk, he motivated the importance of moving away from coal to cleaner sources of energy that are dispatchable, that can be turned on and turned off very quickly. But what we'd like to transition to more of is the scenario on the right. And again, we outlined several of the outstanding research challenges. Suzanne and I are working on these challenges. Eric and Tom are working on educating young people like you about these challenges. And we're going to solve some of these problems, but we're not going to solve them all. And you're going to inherit the problems that we can't solve. And so that's a challenge to you and one that I think would be very rewarding. So that's all I have today. Thank you very much.